I'd like to introduce our speaker. His name is Dave File. He's been the Mercury product manager with Leeman Labs since 2001. And at that same year, Leeman Labs introduced its first system designed to satisfy the needs of U.S. EPA Method 1631. So it's very appropriate that Dave is the one giving the presentation today on the EPA Method 1631 and 245.7. So with that, I'd like to turn it over to Dave. And
thanks, Betsy.
You're welcome.
Thank you so much. Yes, I've been with Teledyne Leeman Labs for about 11 years. We've been manufacturing these instruments for methods 1631 and 245.7 throughout that time. We've picked up a few bits of knowledge from our customers and from use of the systems ourselves and dealing with the regulators that we'd like to share with you. And with that, I'll move straight into the presentation. The topics we're going to be covering today are how Mercury requirements got as low as they are, how to decide which method you should use, some facility recommendations so that you can set up the instrument and sample preparation in areas that will be conducive to doing low-level work, the requirements for method 1631 and the instrumentation to perform the analyses using that methodology. We have an experience, actually we have several experiences in helping people certify the laboratory for the methodology with the state regulators, and certainly like to go through one of those experiences with you, talk about contributions from other laboratories, and round things off with a overview of method 245.7, which is now approved. Many people consider the linchpin for the introduction of the Clean Water Act occurred when the Cuyahoga River caught fire, and it burnt down several bridges that span the river. And this was due to all kinds of organics that were sitting on the surface that got ignited. They were flammables, and it took quite a while to put that fire out. And in the process, it burnt down several spans crossing the river. So that was 1969. Jump ahead to 1987. It took 18 years, but the Clean Water Act was approved and passed into law. And in that act, it mandates that states have to create quality-based control strategies to achieve the water quality criteria, and that each state should set its own water quality criteria standards. The same year, the EPA and Environment Canada focused on the Great Lakes region and came up with an agreement where they would attack the primary sources of mercury entering the environment. Both of these requirements demanded that water quality criteria be established, and the National Toxics Rule established that criteria for a number of toxic pollutants, including mercury. If you look at the criteria for the previous method, the 245.1, which was the cold vapor atomic absorption methodology, it had a detection limit of 200 parts per trillion. So there are a number of categories, both within the Great Lakes region and beyond the Great Lakes region, that demanded lower detection limits. And to that end, the EPA has introduced two methods, 1631 and 245.7, to achieve lower detection limits. EPA 1631 is a method using atomic fluorescence, but also employs a purge and trap to pre-concentrate mercury prior to analysis. The second method that was approved in 2007 is method 245.7. It's sometimes referred to, and you see this in some later slides, as modified 1631. It has very similar digestion as method 1631, but it does not include a purge and trap step to pre-concentrate the mercury in the sample. Method 245.7 is approved only for report limits above 5 nanograms per liter by the EPA. So which method do you want to choose? If you were looking for drivers for that, again, I would recommend that you check with your local regulator to determine which methods they will accept, and furthermore, check what the lowest discharge permit levels are that you need to meet. For most people, the good news is that systems that are on the market today typically can satisfy either method with either no physical change to the system or very minor physical change. This is a pretty busy slide, but there's only a couple of things I want you to take away from it. And the first is that this was a draft that was introduced in 2005 from Region 8 of the EPA for a strategy to control mercury emissions. And if you look on the right, the left-hand column of that table has the different types of samples that will require monitoring. And of all of those samples, there are only 2 that require solely 1631, wastewater effluents and surface waters. And again, this would be where the report limits are under 5 nanograms per liter. Most of the others will either identify it as 1631 or modified 1631, which even at that time the EPA put in parentheses being method 245.7. This was the official letter, the memorandum that was promoted or distributed from the Environmental Protection Agency that announced that the 2 methods were available and that 245.7 was now accepted with the caveat of its report limit. Let's focus for a moment on 1631 itself, just to give you a little background information. It was developed by Nicholas Bloom at Frontier Geoscience Lab, and it's currently in its 5th revision, Revision E. If you're interested in pursuing this methodology, then there are several pieces of information that are available either from the EPA website or from us. If you prefer to get them from us, if it's easy for you, we can provide them. But it is, the 4 items are the method itself, a guidance for implementing and using the method, the related sampling method, method 1669, which tells you how to collect trace level mercury samples. And it also provides a guidance for establishing clean areas where you can do trace metal analysis, including mercury. These are really useful pieces of material that you can get better information on how to prepare for your analysis. One of the key concerns to everyone who looks at 1631 is controlling contamination. And you really need to take a look at the difference between previous detection limits required of the cold vapor technique, atomic absorption technique, which was a detection limit of 200 parts per trillion for method 245.1. And further, if you look at the new methods, 1631E now, its highest standard in the calibration curve typically is only about half of what the detection limit was for the previous technique. And in fact, its detection limit is 1,000 times lower. That challenges you in terms of keeping your environment free from mercury. And even if you have the luxury of using method 245.7, its detection limit also is 100 times lower than the previous technique. So when you're concerned about contamination, you ask yourself, what do you need to do? Is a Class 100 cleaning really necessary? From our experience, it isn't. We've got most of our users in somewhat of controlled environment, but not what you would consider a Class 100 clean room. And they have to be very careful in terms of the contamination sources that they have and how to control them. And we've broken them into 4 areas: reagents, the analyst, the environment, and the equipment. And there are things you can do in each of these areas to help to keep the area free from mercury. If we take a look at the environment, my recommendation, and it is also listed in the guidance, is to use a closed room with controlled limited access. Typically, it needs a doorway into the area, walls that extend to the ceiling, and a solid ceiling. For people who enter and exit from the area, they should be cleaning their shoes, the soles of the shoes, on a sticky pad at the doorway to prevent dust and dirt being transmitted into the area. When you locate your prep area and position your instruments in the laboratory, it's wise to keep it away from the incoming air vents. And particularly if you can bring the air into those air vents from outside the building, that's a real advantage. Typically, the outside air is going to be lower in mercury than you'll find in any of the other areas of your laboratory. Many people consider and do use positive pressure enclosures. These can be equipped with HEPA filters to remove dust, gold filters to remove mercury vapor, and other filters are also possible, such as carbon filters. They're used in the dentist's office nowadays, and it does help to control the mercury in the atmosphere of the laboratory. Metal components that are exposed are best covered. If you can paint any metal components, you're better off, or totally eliminate them. And finally, fluorescent lighting. Although typically the fluorescent lights are sealed, if you have a broken tube or whatever, then you introduce mercury in a level that might take you a while to clean up from the laboratory. So if you can avoid the fluorescent lighting, it's well worth doing. If we look at the analyst, most of this is just common hygiene, but typically if he is provided with a lab coat that's cleaned regularly and used only in this area, then it's probably going to isolate other mercury sources that may be within the lab from the low mercury area. It is important that people wear gloves, but they should be advised not to use ones that have talcum powder to help slide the gloves on or off. Typically latex or such gloves do the job of isolating the sample from the analyst's hands quite well. The third item, some places do use hair nets or masks to isolate further the analyst from the instrument and samples and standards. Typically, we haven't found that to be necessary. We don't use them ourselves, but it is important to consider that if the analyst is ill or if he's got a lot of facial hair, then you may want to use one of these techniques temporarily, one of these devices temporarily. Certainly, if you cough or sneeze, you generate an aerosol, and that can migrate into your samples and cause you contamination. In terms of equipment, only Teflon and borosilicate containers are permitted for the digestion and preparation of your samples and standards. You can use other types of materials at the time of analysis, but you really want to limit the amount of time that those containers are in contact with your samples and standards. I would strongly recommend segregating the glassware so that you only use this glassware for your 1631 operations. And in fact, the EPA recommends serializing this glassware so that if you catch a sample that or a reagent that is highly contaminated, you can identify the glassware that it came in contact with and remove it from the general population. One location that we did provide some certification assistance with had several reagents that they had purchased for the digestion and for the analysis. And typically, the things that you need are deionized water, hydrochloric acid, stannous chloride, hydroxylamine, and a special bromine, bromide-bromate solution, a bromine monochloride solution. Most of these reagents can be cleaned up by sponging. The bromine monochloride solution cannot. So, for those of you who are wondering what sponging is, this is really an important thing for cleaning up your reagents, for the ones that you can clean. And basically what it involves is injecting argon or nitrogen into your sample or solution and bubbling it. I said sample solution, into your reagent solution and bubbling it. In the case of stannous chloride, all you need to do is bubble argon or nitrogen to that solution, and the mercury will evolve from that and clean up by this process. Typically, we use a gas flow of about 5 liters per minute, and we run it for 30 minutes. We have a simple, quick disconnect piece of equipment that has a small regulator on it to control the gas flow and to bubble it. If you have other solutions that you want to clean up, such as the hydroxylamine hydrochloride or the rinse solutions, what you can do is add 1 ml per liter of stannous chloride to that reagent and bubble it in the same fashion for 30 minutes with about 5 liters per minute, and those will clean up as well. We found contamination from water sources to be a concern at this first account that we did this certification assistance with. And the interesting thing was that tap water was actually cleaner than the deionized water that came into the laboratory. In this facility, what they had is they had a central supply of deionized water, and then they had it plumbed to the individual labs. By the time it came to the individual lab where the low-level mercury was occurring, measurements were occurring, it had increased in its mercury concentration such that the counts for the blanks were more than twice as high as the tap water that we ran versus it. By putting a simple polishing filter right at the spigot, we were able to drop the mercury content by about 90%. This is really important in satisfying your blank requirements for the calibration, which we'll talk about a little bit later. Looking at the method itself, again, this is just the front page to the method. I'll give you a summary of the method for those of you who are not familiar with it. The sample can be oxidized and preserved with a bromine monochloride solution. It is shown in the bottom picture here is the concentrate, and 5 mL per liter of that solution is added to your samples and standards, and that will convert the mercury species in that sample to mercuric ions. Prior to analysis, you add hydroxylamine hydrochloride to the solutions, and they will that reagent will remove the excess bromine from the solution. So basically, if you look at the top picture, you can see that to the left-hand side, there's a slight yellowish tint to the solution. And once the hydroxylamine hydrochloride is added, it is clear. At the time of analysis, the sample is mixed with stainless chloride, and that converts the mercuric ions to ground state mercury. And purging that solution with argon or nitrogen will release the mercury from the solution, just as it did when we were sponging the stainless chloride solution. We then use a gold trap to capture the mercury as it evolves from your solution in the argon stream, and we thermally desorb the mercury in an argon stream and transfer it to the fluorescence cell for detection. This is figure 3 from EPA Method 1631 version E, and it's for a flow injection system. This is the first time that they've discussed flow injection systems, but basically it takes the samples and mixes it with the reducing agent in the T, goes to a gas liquid separator, liquid goes to waste, and the vapor is carried on the carrier stream, argon carrier stream, through a soda-lime dryer and onto gold trap, maybe 1 or 2 gold traps, where the mercury collects. And then they're heated, and as the mercury evolves, is released from the gold, it's transferred to the fluorescent cell for detection. One thing that has been a point of contention over the years is how many traps are needed to do this analysis. Is it 1 trap? Is it 2 traps? Actually, in EPA Method 1631, Section 9.1.2, they recognize that for automated systems, the single trap amalgamation is permitted. And you might ask yourself, why were the 2 traps originally specified for the method? And you have to really step back to the manual version of 1631. 1631B was the first one that was generally employed. And it had 2 stages to it. The first stage was sort of sample collection. And you would have perhaps 8 or 10 of these bubblers set up in a hood, and each one would have the same configuration, where they would have a soda-lime dryer and a gold trap. The analyst would add their sample of the standard stainless chloride to the bubbler, and then bubble argon or nitrogen through it. Mercury would evolve and collect on traps. The problem is that each of these would have different traps, and you really then take trap one at a time, put it into the analyzer, and you wanted to move the mercury onto an analytical trap so that the peak characteristics were always the same. The way it eluted from the trap was consistent. So they needed 2 traps to do this. Again, it replaces this sample trap completely with a new sample trap, but the mercury is transferred to the same analytical trap for elution to the fluorescent system. So that was the reason that they needed 2 traps originally. With the continuous flow systems, flow injection systems, as the EPA calls them, you're always collecting the mercury on the same trap, whether you have 1 trap or 2. So it's sort of redundant to have 2 traps. Our original system had 2 gold traps, and the new system that we offer now only has 1 trap. And what it offers customers as a result is very fast analysis times. You eliminate the second evolution of mercury, the second release, desorption of mercury from the gold trap. And we've also been able to increase the sensitivity of the system. If you look at this plot, this is a calibration from 0.5 to 100 nanograms per liter of mercury. And all of the requirements to satisfy method 1631's calibration are all met for this. And it was generated at 3 minutes per standard. It's using a calibration factor algorithm, and this algorithm is required by the EPA. For those of you who do not know what it involves, it's basically you take 3 replicates of a blank solution, you take the intensity for those replicates, and calculate an average intensity for the blank. And then for each of the non-zero standards, their intensities is then subtracted, blank subtracted, and that shows up in this column here. And finally, a calibration factor is calculated by taking each of the blank subtracted areas and dividing them by the individual standard concentration. So that gives you basically a slope for each individual point. And the 2 measurements, or the 2 calculations that come from these measurements are the average calibration factor, which in fact is the slope that you're going to use for the calibration itself, and the relative standard deviation of these calibration factors. And that relative standard deviation is really an indication of how well the curve fits, how linear it is. And it has a requirement of 15%. In this case, we're satisfying it with 5% relative standard deviation. The calibration also has 2 other quality control requirements. This blank intensity, when divided by the average calibration factor, has to report back a concentration for the blank of less than 0.5 ppt. In this case, it came back reading 0.33 ppt, certainly acceptable. And you also have to calculate what the recovery is for your report limit standard. Now, this report limit standard may vary from state to state, and it may also vary based on what your individual permit requirements demand. But at this level, it has to be within plus minus 25% of true. So in this case, we're getting 108% recovery. All of the calibration requirements are met, and the analysis could be continued. One thing to consider is there are a lot of blanks that you have to qualify. You want to know how much contamination are in the bottles you use, how much are in the bubbler systems that in the analyzer itself, how much is in your sampling equipment and other laboratory equipment that you may use. You also need to generate a method blank, which is just a determinant of what you consider a blank sample reads back at versus calibration, and reagent blanks. In this slide, basically what we've done is just taken the low-level peaks up to only 5 nanograms per liter and overlaid them on the same plot. Software allows us to do this. And you can see that from the light blue tracing that concentration or that intensity is much less than the 0.5 that is subsequently generated or any of the higher standards. So this would indicate that this is, in fact, low enough to satisfy the blank requirement of the EPA method. From my perspective, the way I like to prepare standards, I always do it the same way. I make up a large volume of the 0.5% chromium monochloride solution. This basically becomes your diluent or your standards. And the first thing that I pour from that bottle is the blank. The more you open and close that bottle, obviously the more opportunity you have for contamination to migrate into it. So I like to prepare the standards from the lowest concentrations to the highest concentrations. That way, when I'm doing the 0.5 or the 1 or the 2 standard, I've got the cleanest solution for my diluent. And typically, I'll have a intermediate stock standard of 100 or 200 ppt that I make my dilutions from. When you take a look at the instrumentation that's involved to satisfy 1631, it requires a soda-lime dryer. This is a chemical mixture of calcium oxide, sodium hydroxide, and water. And it does a very nice job, not only of removing any liquid phase moisture that may be in there, but also of removing the halogens, hydrogen fluoride or whatever that is produced from your solutions will be captured in this soda-lime dryer. We use the soda-lime dryer, and we also use a secondary dryer, a naphthalene dryer. Now, the soda-lime dryer is required for method 1631, and the naphthalene dryer is required for method 245.7. We use both of them serially to provide the best drying that we can achieve. Naphthalene dryer is basically a permeable membrane. Your wet gas comes in one end, and it migrates through the permeable membrane, and you have dry gas entering from the other side of the permeable membrane, and moisture will migrate from the wet stream into the dry stream. These types of dryers are really good to work with. They're pleasant to work with because they have no moving parts. They don't require any maintenance. They're self-regenerating, and they're able to reduce the amount of moisture in your samples and standards vapors in the gas stream significantly. The importance of this is that fluorescence is much more sensitive to molecular species. Water vapor is a molecular species that will quench the fluorescence of your signal, so you get low intensities if you have water present. It's much different than what is understood in cold vapor atomic absorption. You can have a lot of water vapor in the cold vapor atomic absorption approach. As long as you don't have any condensation in the optical path, it really won't impact the signal that you get much at all. But in fluorescence, it can dramatically drop the intensities. So it's important to remove moisture as best you can. If you take a look at the fluorescence detector, these will be different from manufacturer to manufacturer, but they all have certain similarities. And those are that the source in lamp that produces the emission wavelength is at right angles to the detector. And basically, it emits a wavelength of light at 254 nanometers, which the mercury atoms, as they enter the fluorescent cell, can absorb and then re-emit, and that's fluorescence. When they re-emit that light is re-emitted in all directions. So most systems will have some sort of mirror device to help promote the emission traveling through to the detector. In our system, we have a mirror on the opposite side of the fluorescent cell. We have a collimation filter. We have focusing lens and an interference filter that limits the wavelength. These things are going to be fairly similar on many systems, but the size of the fluorescent cell and such will vary, and the shape of the fluorescent cell will vary from system to system. So again, getting back to our experience in state certification, I'd like to take this one account and talk about it. We've published a paper jointly with Denise Stalby of Oxford Labs several years ago covering this work. But in 2003, North Carolina announced that as of September 1st, anybody who was reporting concentrations of less than 0.2 part per billion had to use method 1631. The Oxford Lab Management had a number of customers who were already supplying samples and needed to go to levels lower than the 0.2 part per billion that method 245.1 cold vapor AA method satisfied, and they asked for Oxford Labs to provide the capability to report these results. So Oxford Labs, they did the logical things. They did the literature search. They made modifications to the facility to promote a clean area, and they purchased the instruments and accessories that they needed to do the analysis. So exactly what did they do for their area? They set aside a limited access area with a doorway and sticky pad at the doorway. For them, they put a window in the door and instructed others who might be entering into the lab to gain permission from the operator before they entered. They painted the walls. I believe they use sulfur-doped paint, about 1% sulfur in the paint, will help capture any mercury that may be migrating through the walls. They brought the air in directly from outside the building. This, again, it's an important thing, and it really does reduce the amount of mercury typically that you'll find in the area. They also purchased 2 enclosures, positive pressure enclosures, and they installed a deionized water supply into the laboratory. The systems that they used, the enclosure systems that they used, were air clean 600s. These are pretty nice enclosures. They have multiple levels of access to the work area inside. They also are equipped with a pre-filter and a HEPA filter. Again, I would stress that for those of you who are contemplating method 1631, the HEPA filter in these enclosures really is designed to capture dust particles. If you have free mercury migrating or in your atmosphere, it will move through the HEPA filter without any problem. So one other area that we recognized a problem at the site was containers. We were providing them with solutions both in Teflon containers and fluorinated polyethylene containers. These are containers which are filled with fluorine gas for a period of time and allowed to react with the fluorine gas. Those fine containers just did not do the job. There was too much contamination. So we've actually stayed with Teflon and glass only for reagents. The one item that you cannot clean up, and this was problematic for them, is the bromine monochloride solution. It's added to samples and standards at 5 mLs per liter, typically. We did a check on how much mercury was in the bromine monochloride solution by adding and measuring as blanks solutions that had 5, 10, and 20 mLs per liter of the bromine monochloride solution added. And we were able to determine that we were getting about 1,000 counts added to the blank for the bromine monochloride solution. Interestingly enough, the solution was working well, but they decided to prepare a new solution, and right out of the bottle, it was unacceptable at about, I'm thinking that's probably around 1.5 part per trillion of mercury that those blanks produced. They discarded that solution, which is the only thing you can do, and prepared a second solution, and those blanks were acceptable, were below the 0.5 requirement of the method. Another area that you have some flexibility with is sample containers. There are a number of suppliers that will provide you with sampling bottles that are double bagged, Teflon lined screws, top, and also certified to be free of mercury. One of these customers, or one of these suppliers, is Environmental Sampling Supply. Also, I know that QEC offers the same type of pre-qualified containers. This can take some of the burden off of cleaning your glassware yourself and maintaining records of cleanliness. So they thought they had, done their homework. They had built the area that they're going to do the work in, and they had purchased the instrumentation, and they thought they were ready to begin. So if they looked at the EPA's requirement for demonstration of laboratory capability, the left-hand table tells you the items that are required in that section of the method. And the right-hand table basically is a listing of the types of samples that need to be run to satisfy these QC requirements. The next few slides are going to handle the results that were generated basically from running this sequence of samples. This work was done in 2003. It was done on the original Hydra AF Gold Plus. It took about 6 to 8 minutes a sample to complete, primarily because we had 2 gold traps, and we evolved the mercury off both gold traps every time. And we also required a 40 ml sample volume to be pre-concentrated on each of the gold traps. The end result is about 4 minutes of uptake time, and followed by another 2 minutes for each desorption process. So it ends up being about 8 minutes a sample. This now can be done in about 3 minutes, and we've made some changes to the system that allows us to meet the same performance criteria in 60 seconds of uptake time, and again, with just 1 gold trap. So taking a look at the requirements, what you'll see on the next few slides is this blue area is going to identify what we're showing in the table from the sequence that was run, and then we'll talk a little bit about the results in the sequence themselves. So we needed to generate a calibration curve. When we did so, we found that it was acceptable with a good linearity. The percent RST on the calibration factor was 9%. It has to be less than 15. The average blank was 0.47. It has to be less than 0.5. Subsequently, through use in just familiarity with the technique, they typically got down to about 0.22 for their average blank. And finally, the recovery on the report limit standard came back at 113%, which needed to be within 75 to 125. Moving on, the next thing we did was we did a method blank initial precision and recovery check, and a secondary standard check, and method detection limit. The data shows that the blank was acceptable under 0.5, again, reading back at 0.25. The IPR is a 5 part per trillion standard. It came back reading 4.8. We generated another calibration standard from totally different source mercury that came back reading about 85%. It was a 10 part per trillion standard. It read back 8.5. There actually isn't any criteria for what is acceptable or unacceptable that I could find for this quality checks sample. And finally, we did 7 replicates of a 1 PPT standard and found that we had acceptable method detection limit and good recovery and standard deviation on those samples. And the final things in the sequence were method blank. They do a repetition of 4 ongoing precision and recovery checks, and then spikes and spike duplicates on the sample. And these results generated showed that we got a good accuracy and precision on the ongoing precision and recovery check. Again, it should be 5. It came back reading 5.35 or 107% recovery. The sample spikes had a good recovery at 102%, and the relative percent difference between the sample spike and the sample spike 2 was 2.17%. They were really excited about this. They tabulated the results the next morning, drove up to the state regulatory board, and were certified by 2 o'clock that day. Well, moving on to method 245.7, why would you consider 245.7? What are its pros and cons? Certainly it's faster than 1631 without the gold traps, and it's less expensive without the gold traps. And contamination is less troublesome. You're working an order of magnitude higher in concentration for your report limit standard. So it's much less of an impact. On the negative side, not all states have accepted method 245.7. It is less sensitive, and the EPA only allows it to be used above 5 nanograms per liter. But again, it has pros and cons. Taking a look at the method in comparison to 1631 at sort of 50,000-foot view, both are approved, again with the caveat on concentration for the report limit on 245.7. They both have, again, wide linear dynamic range. This is reported to 250 ppt for 1631. Nobody goes higher than that, I don't believe, using this technique, but it actually is much more linear than that. The cycle time is 4 to 9 minutes in 1631, a lot faster in 245.7. It's 2 to 3 minutes. And again, the required NDL, MLs, they're about 10 times higher in 245.7 than 1631. So it often can be a lot easier to satisfy. Looking at precision for the 2 techniques at the ongoing precision and recovery concentration, you can see that they are quite similar in RSD. If you take a look at the standard deviation itself, they're even closer. You have to remember that the OPR for 1631 is 5 part per trillion, and the OPR for 245.7 is 10. So if you take that into consideration, then the standard deviations of the readings are quite close. And all of the interferences, this section is almost taken word from word from 1631 as it applies to 245.7. It's all the same interferences. Again, talking a little bit further in depth about 245.7, it employs a calibration factor algorithm as 1631 does, but in this case, it doesn't use blank subtraction. And again, on the calibration, it has a requirement for linearity that's the same as 1631. It has the same accuracy or recovery requirement but again, 5 times higher in concentration for your port limit standard. And the ongoing precision and recovery conformation is at twice the concentration of 1631. So again, everything is lifted a little bit in terms of concentration. Well, this is what we get for a plot using calibration factor on the method 245.7 configuration. And we've actually taken this plot and added a standard at 1 part per trillion. And you can see using this calibration factor algorithm, the readback even at 1 part per trillion is quite good. It's 1.1 nanograms per liter. And again, the percent recovery is good. Again, the blanks quite small. In this case, it doesn't have the same significance as 1631. And the linearity is well within the requirement. So this was accepted even with the 1 ppt standard, which is lower than the port limit offered by the EPA. I want to compare that number to other ways of doing the calibration. And this is the same data, the same intensities, same standards, but using a straight linear fit, which is going to apply the same error to all of the standards. And you can see that at the high end of things, 100 part per trillion standard is 99.5, quite good at that level. But at the low level, at 1, it's 0.5, it's 50% off. So that's really the impetus for using calibration factor. And we offer a weighted linear calibration as well, but even in this case, you can see that the readback on the low standard isn't quite as good as the calibration factor approach. Again, on this one, you can see that we put more weight on the low end of the curve, and that comes closer, but the high end of the curve tends to walk away from the value. This is very typical of these calibration algorithms. So if you want the best accuracy at the very low end of the curve, calibration factor approach is really what you want to use. Again, I've talked a little bit about linearity, and certainly we promote that the system can be used either in the, and we have used it in the low PPT level ranges as well as up in the part per billion range. This plot shows calibration to 50 part per billion. I would strongly advise you not to try to create a calibration curve that is going to transition through all of these concentration ranges. If you do, you'll lose all the significance at the low end, and at the same time, you will have a lot of trouble trying to get back to an accurate reading at the low end after high concentration samples are run. So again, you can work in the high range if that's where your analysis is based. You can work at the low end, but don't try to do both of them at the same time. I just want to go through a few of the requirements for method 245.7, and then we'll finish the presentation. These are from the method itself. The requirements are the determination of an MDL, freedom from contamination, how low does the blank read back. And you can see that, again, these are almost a factor of 10 higher than 1631. In the initial precision and recovery checks, you do 4 replicates, but it's at twice the concentration. And we'll take a look at what we get for these requirements for demonstration laboratory capability. And we're also going to recognize that just as in 1631, you do have, during continuing analysis, the requirement to run an independent standard to confirm that your source mercury standard is accurate. You're going to do ongoing precision recovery every 20 samples. And again, this is a 10 part per trillion standard. And you're going to run a matrix spike and spike duplicate every 10 samples. Well, when we looked at the method detection limit for 245.7, we ran a 0.2 part per trillion standard. Its mean was about 0.3, and the detection limit that was calculated from these 7 replicates is 0.31 part per trillion, well below the 1.8 that's required. We also did acceptance initial precision and recovery check, and this requires 4 replicates of the IPR. It came back reading 91.1%, right in the middle range of the acceptance limits. And the precision on these readings was 2.2%. Again, much less than the 16% that's allowed. So to wrap up, what should you do if you're considering taking on method 1631 or method 245.7? And certainly I would start off by asking questions. Who makes your regulatory decisions for you? What method is needed? What methods are permitted? What levels do you have to work to? And will each of the methods satisfy those levels? I'd really recommend you take time to prepare beforehand to complete the analysis. Decide well in advance of purchasing an instrument or whatever, where you're going to set up your preparation areas and analysis areas. And I would recommend that you isolate operations as much as possible. Again, we've talked about that before, and I won't get into that again, but there are a lot of things that you can do to make sure that that environment is clean. I'd like to acknowledge the help that I've received from a number of our customers. Mark Boost at Test America is really an expert on all things, I'd say analytical, well beyond the mercury environment. John Melvin at Environment One was one of our earlier customers, and he actually had a problem with his environment because his area used to be used as a dental office, and we recognized in that location that dust was a real problem for him. And subsequently, he started preparing his standards and samples outside the building completely, brought them in and put them into the enclosure based analyzer, and then was able to get good results. John Pastor at Meritech Labs helped us, as well as Stephanie Scheringer at City of Gastonia. These were all early players in the 1631 experiences that we had. And again, William Sherman at Oxford Lab and Denise Stalvey at Oxford Labs, they worked with us to go through the whole certification procedure, and they were a great help in us learning what's required to get certified. With that, I'd certainly like to thank you all for participating in this webinar, and open it to any questions.